Okay, so what I've done, I've gone through and picked, what do we have? 7 topics here that I think are probably maybe some of the most difficult or most complex topics on the exam. Obviously, this isn't going to cover everything on the exam, but I think these are your biggest topics, again, most complicated topics. So we can see switch connections, different voltages. I'll explain what that means when we get there. General receptacle layout, kitchen receptacle layout, parallel circuit calculations, burial depths, and then wire sizing. This one's kind of a minor thing. There's not a ton of them on the test, but it's a very important topic nonetheless, and there is a few, so we should definitely cover it. So if we sort of dive in here, our switch connections, right? And what I mean by that is you're going to see, a couple problems where there's some switches, some diagrams, some pictures, and they say, where do your travelers connect? Which screw should go to your light? Which screw should be the power in? And I think the best way to look at that is let's just do some quick review on your switches, right? So we see this guy here is a single pole switch. We know that because there are 2 screws. Not counting your ground screw, there are 2 screws, right? Single pole switch has 2 screws. Next up, we move to our 3-way switch here. Not counting our ground screw, we have 1, 2, 3 screws for wire connections. 3-way switch has 3 screws. We'll come back and talk about them here in a bit. We move over here to our 4-way switch. We know this because we have 1, 2, 3, 4 screws, not counting your ground screw, right? So down here we see a diagram of a 3-way, 4-way, 3-way switch setup. First thing to note here to remind you guys of is for a 3-way, we have 2 screws that are going to be one color, generally gold. Then we have another screw that is a different color, generally black. That screw is known as your common screw, your point screw, your line screw, load screw, whatever the case is, that screw is different, right? This screw essentially goes to your light fixture, or it is power in from your source. The other 2 screws are for your traveler wires, right? So in this example, we have, power coming in over here. Black wire comes in, it goes to our black screw. We can't really see that it's black, but it goes to our black screw. Then coming off these other 2 screws, which would be equivalent to these 2 right here, we have what's known as our traveler wires, right? So traveler goes out here, a red traveler and a black traveler go through here along with our neutral, right? The travelers land on the 4-way switch, pairs go across from one another. Again, travelers here on the 4-way, all the 4-way switch has is traveler wires, but they go out into the other 3-way switch. We have travelers coming in here and here. Once again, that would be equivalent to here and here. Then we have our common screw is our power out to our light fixture. So I think those items there are when you're sort of armed with those pieces of knowledge, I think that'll get you through what we need to know for the exam. Next up, we're going to look at this sort of different voltages scenario. And this is one I told you guys is not going to go away as long as you're in this class. Different voltages, what do we mean by that? Something is rated at one voltage, we are going to operate it at another voltage. What happens to the resulting other values? So in this case, this thing, whatever it is rated 240 volts. If we operate it at 240 volts, we will get 2,000 watts out. What happens if we only operate it at 208 volts, right? Well, let's find out. So how do we solve this problem? The first thing we need to do is determine resistance based on the original values. That's the only thing we can do in this case. We know that at 240 volts, this thing would put out 2,000 watts. We have watts, we have volts. We need to find resistance. Resistance is the only value that's not going to change no matter what voltage we apply. This goes back to first semester stuff, so hopefully this is boring by now, right? But our volt, we know voltage 240, we know wattage 2,000. We can come to Ohm's law here. We're looking for resistance. We can say E squared divided by P will give us R. So let's go ahead and look at that. So we can say E squared, which is going to be 240. So we'll just do 240 times 240 divided by P, which is 2,000. we get 28.8 ohms, right? So in this case, we would have 28.8 ohms, right? So we're operating at 208. So the only value we can carry from this portion down to this portion is our 28.8 ohms, right? So we have 28.8 ohms. And now, lucky for us, we have two values. We have the 208 volt that we're going to operate it at. We have the 28.8 ohms that we just calculated, which means we can now find the other two values using Ohm's law, right? Let's find the wattage here to see how it compares in this case. So if we're looking for wattage, we have volts, we have ohms. We can say E squared divided by R is going to give us P. So we'll go, okay, that's great. We'll say E squared, 208 in this case, squared, divided by R, 28.8. So we now know that this thing, this item, if operated at 208 volts, will only put out 1502.22 watts, right? So how does that shake out accordingly? Well, if we operate it at a higher voltage, we get a higher wattage. If we lower the voltage, the wattage lowers accordingly as well. So again, while we're here, let's find amperage here too, because it's just as easy. So again, given the original 208 volt, 28.8 ohms, we can go, okay, what's the amperage? We can now say E divided by R according to Ohm's law, right? So we can go 208, which is our E, divided by 28.8, which is our R, we get 7.222 amps, right? And coincidentally, how many amps would this thing have given us if we operated at 240? Well, we can find that out by doing, P divided by E, right? We're looking for amps, we can do P divided by E right here, right? So we're going to go back to the original. This is just out of curiosity, right? So if we did 2,000 watts divided by 240 volts, this thing would have put out 8.33 amps, right? So again, we can see because we have a higher voltage, we get a higher amperage output. Because we have a lower voltage now, we're going to get a lower voltage output. The key to that one is fixed resistance, right? Find your fixed resistance right away. As soon as you see a problem like this, you should be thinking about finding fixed resistance, right? As soon as you find fixed resistance, couple that with the new operating voltage, you got two values. Now it's just an Ohm's law problem, right? Okay, moving on, let's hit our general receptacles, right? And hopefully you guys can see this. I'll zoom in a little bit. But essentially, whenever we talk about the layout of receptacles, when I say general receptacles, I mean basically not the kitchen, not the bathroom, not the garage. We're talking about your normal rooms, right? Your living rooms, your bedrooms, that kind of thing. How do we lay those receptacles out? Well, that's essentially a matter of 210.52A, right? Everything under A is about where that comes from. And here's the gist of it. So first of all, if you're not sure, look it up in 210.52A, right? But here's the gist of that code. It's going to read no wall space can be more than 6 foot from a receptacle, right? No point measured horizontally along the floor line of any wall space is more than 6 feet from a receptacle. Again, what does that mean? How far can we have between any two receptacles? The answer is 12 feet right here, right? And how does that sort of shake out? Pick a point along the wall line arbitrarily, any point in here. If I go 6 feet in one direction or the other, I need to hit a receptacle. So even I come right in the middle, right? Exactly 6 feet. I go 6 feet this way, I got a receptacle. 6 feet that way, I got a receptacle. If I come down here a little bit, let's just pick this point, right? Well, we know if it's 12 feet here, if I'm all the way over here, this is going to be less than 6 feet. Doesn't matter that this one's, 8 or 10 feet away. This one's less than 6 feet. We're good. Again, you think about that lamp. You sit on the floor. It's got a 6-foot cord. No matter where I put that in this wall space, I need to be able to hit one of these receptacles with that 6-foot cord. And that's the point of that code. That's exactly why we have it that way, right? Sort of the other side of that is a door is going to break up wall space, right? So our wall space starts right here where this door stops. So they start here, they go 6 foot to the first receptacle. They can't go 12 foot because, again, any wall space, so anywhere in here I go, I need to have a receptacle no more than 6 feet. Again, I can put that lamp with a 6-foot cord right here, It'll stretch over here to that receptacle. I'm not going to sit it in front of the door, so we don't have to worry about that. Now we look at this space between the two doors here, right? It's 1'11". They don't have any receptacles here. Why not? Reason being is right here, right? 21052A2, wall space. As used in this section, the wall space shall include the following: any space 2 foot or more in width measured around corners, right? So any wall space 2 foot or greater, we need a receptacle. If it's less than 2 feet, we do not need a receptacle in that wall space, right? So that's why we don't have one right there. If this were 2 feet or 2 foot 1 inch, we now need that receptacle. Last thing to point out, notice they are measuring around corners. Corners do not break up my wall space. It's still considered, continuous wall space. That's why we have sort of this, 10 foot 1 from here to the corner, and then they keep that measurement going. They add another 1'11", which gives us 12 foot. That's where they put that last receptacle, right? Okay, so we'll end this portion of the video on this item here. Same logic, except now we're talking about kitchen countertop receptacle spacing, right? Same theory, same logic, but the measurements are going to change a little bit. Basically, we're exactly the same, except now instead of the code reading no wall space can be more than 6 foot from a receptacle, the code is going to read that no wall space can be more than 24 inches from a receptacle, which would then translate to our receptacles can be no more than 4 feet apart from one another, right? So once again, in this case now, what breaks up wall space? Well, it's still doors, but we also add the kitchen sink breaks up your wall space. Your range cooktop breaks up your wall space. So your refrigerator here in this case breaks up your countertop wall space. So what do? We start right here at this, bad example. Let's start at the sink here, right? We're going to go 2 feet. We're going to hit our first receptacle because no wall space can be more than 2 feet from a receptacle, right? So we go 2 feet from the edge of the kitchen sink. We have our first receptacle. Then we're going to measure another 4 feet around the corner to hit our second one, right? Same story. What constitutes a wall space? In this case, it's anything that is 1 foot or larger. Whereas before, in the living room, in the bedroom, we were 2 feet. Now over here, it's 1 foot. Whoops. So over here it's 1 foot. So again, this is a 1 foot space. So we have to have a receptacle. Were this less than 1 foot, if it were 8 inches, we do not need that receptacle, right? So we'll take a break here, break up the video. Part 2, we'll jump back in with our parallel circuit calculation.